Hi, this is a quick sound check. Can someone write yes if you can hear me loud and clear, please? Thank you. All right. Yeah, so today we'll be talking about hidden Markov models. And let's go over the logistics quickly. Most of these logistics or announcements are from last week, so I'll not linger on them. For this lecture, stay back until I end the meeting today, because after I'm done through the content on HMM, I'd like to spend a few minutes on going over assignment 2, and especially I'd like to redo the multi-headed attention part, because there are some questions about this on Piazza. So yeah, please stay back until we actually end the lecture. And next week is reading week break, and I would encourage you to attend the tutorial this Friday on assignment 2, and hopefully you can utilize the reading week break to complete assignment 2. All right, let's get started. So the lecture plan today is this. So today we'll be talking about observable and multivariate models, introduce HMM, and the fundamental tasks hidden Markov models are used for. The following 2 lectures, which will be in person, we'll be going over some concrete algorithms using HMMs, like the Viterbi algorithm, and expectation maximization algorithms like Baum-Welch. So what is the observable Markov model? It's essentially a statistical model that assigns a probability to a sequence of events, such as word tokens. It treats the sequence as something evolving over time, where the probability of the next event, such as the next word token, is conditioned only on the previous events or the previous word tokens. The model makes the Markov assumption, which means the probability of the next event is conditioned on a fixed size of recent history. We saw this assumption back when we're talking about n-gram language models. And indeed, n-gram language models are a type of observable Markov model. We can frame a bigram model in the more general context of Markov models with this example over here. So essentially, if we want to calculate the probability of this sequence, ship, ship, pass, ship, tops, then from our n-gram language modeling knowledge, we can, assuming that it's a bigram model, we can calculate this probability by calculating this probability over here, that ship given start of sequence, then ship given ship, pass given ship, and lastly, tops given ship. So we can also conceptualize this idea graphically by assigning a state to each of the observed tokens. So we can start for a running example, if you have n states, our n value would be 7, where each of these observed tokens belongs to one individual state. And we have discrete time steps, t equals to 0, t equals to 1, and so on. And on the tth time step, the system is exactly in one of the available states, qt. And we can start at any state. The probability of starting with a particular state s is given by our pi function over here, pi s. So essentially, the probability of starting, let's say in the node ship would be given by pi ship. So at each step, we must move to a state with some probability. And here, an arrow from state qt to the qt plus 1 represents the probability of qt plus 1 given qt, which are denoted by these arrows over here. So for example, like if you take the ship node again, the red arrow represents the probability of self-traversal, coming back to ship, the probability of being in ship, observing ship. And then the yellow represents probability of observing tops coming from ship, and so on. One thing to notice is that If two nodes are not connected by an arrow, that means there is no transition possibility. Thus, the transition probability is 0. This is exemplified by this probability of frock given ship is 0 because there is no transition possibility between ship and frock. So there's a question, are these slides on Piazza? The slides should be on Piazza. However, in the last section, I was told that the Piazza link might be broken. So if you want, I can upload a copy of it here in the chat if that is helpful. So let me know if you want me to do that. Okay, so I have uploaded a copy of the slides on the chat. So there's a question, is it by accident that each token only has 3 transitions? No, it's just an arbitrary illustration. I mean, there could have been more. So for example, the ship could have one arrow coming from ship to frock, but essentially it has to be a valid probability distribution. So the probabilities of all the outgoing arcs must sum to 1. But it is just an arbitrary illustration. There could have been more arcs. So. And yeah, so the only condition is that the probabilities should sum to 1. So in this case, if we sum up all the outgoing probabilities from this node ship, it has to be 1. And another example is for the tops node, all the outgoing probability arcs should sum to 1. And so if we had another arc or outgoing probability or transition from ship to frock, in that case, you know, would just have like another probability of frock given ship plus these 3 existing arrows would equal to 1. So using this graph, we can generate sequences by doing a random walk in the graphs. So if you do a random walk, we'll generate sequence by transitioning between the states. And we can also estimate the observation likelihood of a given path. So, but what happens when these probabilities of observing words dependent on some other variable like our moods? So here we have 3 moods. Let's call this disgusted state. This is unhappy state, and this is happy state. And the probability distribution of observing a word token is dependent on which state we're in. So you can also call this table over here as emission probability. And so for example, for this table over here, the emission probability of pass, given we're in this disgusted state, is 0.05. And also, this variable, this mood variable can change over time. So basically we'll have a state transition probability now that if we're happy 1 second and we're disgusted in the next. So in this case, our states would be our mood and our observation would be words. And this is essentially a multivariate system because before, instead of having just the observation, we have another variable, which is state. Thus, it's a multivariate system. And let's take a look at how we can calculate the probabilities of our observations in such a system. So for observable multivariate systems, we imagine that we have access to our own emotional state. So I have access to my emotional state. And if all the data are completely observable at every time step, for example, in this case, we have the observation sequences as mother, frock, and soccer. And we also have the states that each of these observations corresponds to. So everything is observable. So this is an observable multivariate system. And how do we calculate the probability of a sequence in an observable multivariate system? It is pretty straightforward because we have all the data and we have our probability tables. So essentially, we just calculate the probability of a state transition from let's say time step I-1 to I, and the probability of observing word token I in being in that state at time step Q. So essentially, like here, the orange is our emission probability table, and the arrow in blue is our state transition probability. So on the bottom is the concrete example of this. So let's say we have this observable multivariate system with the sequence tokens as ship and pass, and our state moods being happy to disgusted. So then the overall probability of this would be just the initial probability of being in a happy state multiplied by observing the first word token, which is ship, given we're in a happy state. And then we have a state transition probability from happy to disgusted multiplied by the probability of observing pass, given we're in the disgusted state. And the way we can learn these probabilities, it's basically like the same as before. As we have seen in language modeling, we simply do a maximum likelihood estimation from our training data, and that should allow us to populate our state transition probabilities and our emission probabilities, which are the only two things that we need now to calculate this observation sequence when it's an observable multivariate system. However, problem can arise when we have hidden variables, meaning that we don't know which state we are in. And in this case, how can we compute the probability of observation sequence? Even then, this could happen during both testing and training. And this kind of hidden variable phenomena is omnipresent in most processes that we see. So for example, you can consider, in fact, the word representation is considered as a surface form or surface representation, whereas it is considered that word tokens are on the surface, and it is the output of a hidden phenomena from a hidden underlying system. So words are the outputs of a hidden parts of speech categorization or parts of speech variables. French phrases can be taken as the outputs of some hidden English phrases. Speech sounds can be the output of hidden phonemes, etc. And this is in other fields as well. We can consider encrypted symbols as the output of some hidden messages, where genes are the outputs of some hidden functional relationship, weather as being the output of some hidden climate conditions, stock prices as the output of some hidden market conditions in finance, and so on. So how can we principally define such hidden phenomena? And that's where we have the definition of a hidden Markov model, which is specified by 5-tuple, given by S, where S is the set of all states. With a running example, this would be the moods. Then we have W, which is the output alphabet set, which could be our vocabulary in a language model. And then we have the parameters of the model denoted by theta, which is represented by pi, and pi is the initial state probability. A is the state transition probabilities between states, and B is the state output probabilities of a word token, and this is also known as emission probability. So BIW simply means that the probability of emission or observing W, alphabet W, in state I. And the output of hidden Markov model is Q, which denotes the set of state sequence, and large omicron, which denotes the output observed output sequence. So now we can model a process in the world using hidden Markov model, and we can also synthesize data An example, we can generate data after we have modeled a world process using hidden Markov model as a representation ontology. So one example algorithm would be this, that we start at time 0 and we get our initial probability of being in a state from our initial probability table. And then we basically emit the symbol with the probability of the emission probability of observing, let's say Omicron 0 is observing some word token W in our current time step, and then we can sort of like loop over certain time steps, and we can basically use this. We can go from state QT to the next state using our state transition probability, and then emit a symbol with the probability of the emission probability of that token, and then just continue like that. So how can we use hidden Markov models or HMMs in real world? So essentially, there are three main tasks that at a high level that HMMs can be used for. So we look at some of these fundamental tasks. The first fundamental task is essentially the problem that we saw a little while ago. How do we efficiently compute the likelihood of a particular observation sequence given a model, given a HMM model? So we have done this in language modeling, where we're computing the probabilities of word sequence using n-gram models. And usually this probability is useful as a means to some other end, meaning its use in some downstream task. So and the second fundamental task that we have is the task of inference. So this is when we have observation sequence Omicron and a model theta, how do we choose a state sequence Q that best explains the observations? And you can think of this as also like a classification task, in the sense that given some observation, or so let's say given some observed pixels, we're actually classifying that as coming from the state of being a cat or a dog or an airplane, etc. And the third and the last task we'll be talking about is the task of training. Essentially, given a large observation sequence, how do we choose the best parameters that explain this data? So this is essentially the task of training, where we want our parameters to be set so that the available training data is maximally likely. Yes, it is essentially. Yeah. Okay, so for the task one, let's delve into a bit more on task one, where we're trying to compute the probability on observation. So as you can see that if we have an observable model where we have the joints, our sequences of observation and states, then it becomes a straightforward task like we have seen before. We just basically like multiply with our probabilities of being in initial state Q0, then the emission probability of the first observation, then transition probability of going to the next state, and then multiplying by the emission probability of observation in that time step, and so on. But it's harder when we don't have the state sequences given to us. So in that case, how do we find the probability of our observations? So the solution then becomes we have to sum over all possible state sequences. Yeah, so to naively do this, we will, to get the probability, we will directly sum over all possible state sequences. And as you can imagine, that it will be computationally infeasible. So for example, let's say we have an observation sequence of length t, and in each state sequence, it actually involves 2t multiplications, one from the state transition, one from the emission observation, and one from the start state, and -1. And then there could be up to n to the power t possible state sequences, because at each time step t, you have n different choices that you can make. So overall, it becomes like a O n to the power t process which is intractable. And the way we can solve this is by using dynamic programming, where we cache the results of subproblems, and then we can compute the entire result. And in order to apply dynamic programming, we will present this problem, or we will structure this problem in a certain form or structure, which we call trellis. And it's essentially a trellis, or in some branches of ML, it could be also like the tabular form. So here we're just representing the arrays of state versus time. And remember this notation that that any element at IT is represented as alpha IT, which is the probability of being in state I at time t after seeing all observations to that point. So this essentially equals to the probability of observations from 0 to t and being in a state I. And yeah, so this is a visualization of the trellis. It resembles the state diagram we used when talking about first order Markov models, but we have unrolled it in time. Each row in the diagram corresponds to the same underlying state, but we use the columns to indicate what time we're visiting that state in. The arrows always point from left to right into an adjacent column, signifying that we're transitioning from a state at time t to t+1. And we are also assuming no zero probability transitions exist here. So every node points to all adjacent nodes. So because we're asking for the probability of the same observation at a given time, we can group the transition probability and emission probability into one edge. So for example, here, like here, for this yellow node over here, we are essentially saying that this is the summation of all the transition probabilities from all these nodes, all the end nodes in the preceding time step. And then when we're in the yellow node, this is and we multiply that with the emission probability of observing observation 2 while being at state 3. Okay, so with this yellow node as our running example, let's take some of the paths that we can take in order to reach this node over here. So we can take alternative paths through the trellis. So here's one example, orange path, which starts at S1 and then goes to S3 at time 1 and then goes to our time 2. It comes back to state 3 to our yellow node. We can also take another path from state S1 to Sn to S3. Similarly, like this is another path in red where we're going from S1, S2 to S3. Now with this path over here from S2 to S3, this green node over here, we have already computed a path previously through this node. Well, coming from S1, so from this red path here, we've already computed this path. So essentially, you can get the idea that I'm trying to get at the subproblems, which sets it up for solving as a dynamic programming problem. So, for example, like if you consider this yellow path here, each path through this, so basically from this blue node to here, each path will have the probability of some probability of being at that node, the probability of being in this node times the transition probability from state 2 to state 3, and then the emission probability of observation 2 at time 2 being in state 3. So essentially, we have found a subproblem that we can solve as like this. So this subproblem over here, that is the probability of this blue node over here, is essentially this can be denoted from our previous definition of alpha to 1, that is being in state 2 at time 1, which is essentially the summation of all the probabilities from the preceding time step, and so on. Okay, so this slide we just capture of the preceding few slides, the illustration that we did, and essentially, yeah. So to compute the probabilities of the black node and the yellow node, I need, among others, the probabilities of the orange node and the purple node. And the idea is that, as in dynamic programming, that once I compute the probability of this orange node, I save it so that, like, when it comes up in some other path, I don't have to recompute it, but I just use the cached value. Yeah, so we'll be looking at techniques like the forward and backward procedures that uses this intuition of trellis traversals. So the forward procedure essentially computes our alpha IT at each time step by using the definition where we have all the we have seen all the observations until that time t, and we are in state I at time t. So the way we do is we solve the subproblem of alpha jt minus 1, that is the probabilities of each of the nodes in the previous time step. And then we use the knowledge of that state transition table and our emission probability to calculate alpha IT. So we compute the trellis from left to right because of the temporal sequence convention, and from top to bottom just as a convention. We could have done it equally from bottom to top, doesn't matter. Two things to remember is that at time t, our observation t is fixed and known, and alpha IT, we're agnostic of whatever happens in the future. So, I mean, this is a classic dynamic programming setup, and we can compute this left to right or top to bottom. The three main steps in the forward procedure. First is initialization, where we compute the nodes in the first column of the trellis or when time equals to 0 using our initial state probability pi that we have. And then we use induction, where we iteratively compute the nodes in the rest of the trellis using dynamic programming. And in conclusion, once we have calculated until the last column, we sum over all the nodes in the last column of the trellis, and that is our output, that is our answer, or that is our desired answer. Okay, so let's look at an example. So this is an initialization of the forward procedure. So this yellow node over here is showing alpha I0. So this is alpha here would be 3, and we're in time step 0. So the way we do this is we take the initial state probability of being in state 3 given by pi 3 for this yellow node, and then we take the emission probability of observation O0, or our first token observation, and essentially, yeah. So we do this for all the n states. And here, this is an induction step of the forward procedure where we are calculating, the probability of being in some state j. In this yellow node example, this would be 2, and essentially we sum all the preceding time steps values, and which was in the type step 1 we had calculated in our initialization. We know all the values at time t0 of so for example alpha I0, and then we multiply the state transition probability. So for example, if you're coming from state 1. So then in that case, it would be like state transition probability of state 1 to state 2. And then we multiply that by the emission probability of observing the observation at the time step t+1 from our emission probability table. And yeah, so and so on. This is actually, yeah, so this is depicting a clearer version of what's happening at time step t+1. So this is exactly the summation of all the preceding states in the preceding time step. And finally, in the conclusion, yes, there's a question whether the observations are fixed. Yes, the observations are fixed. That was by assumption. And the final step, or the conclusion, we essentially sum over all the final state, which is this orangish nodes over here at time t-1, because we're 0 indexed. Okay. And here is a toy example with the description that with the discussion, and let's try to compute the probability of observing the sequence mother, frog, and ship. And so essentially, and we have 3 steps as with our running example. On the right-hand side, this is our state transition probability table or figure. And we have our initial state probabilities given. So in the initialization step, what we do is we compute the probability of the starting in state I and reading the first word there. So for example, like if we take observing mother in a disgusted state, then the probability is essentially, so the probability of starting in disgusted state is 0.80. From this table over here, and then we multiply that by the emission probability of mother in a disgusted state. So yeah, so I was so where does this 0.1 come from? I was confused, but essentially this is from that emission probability table that we saw very early in the lecture in the running example, I think in one of the initial slides. So essentially just consider that this is coming from a table that we know the value to. So we initialize this as 0.08. And so on. It's basically like, yeah, we just look at the initial for the last happy state. The probability of starting with the happy state is 0, so it becomes 0. And then we look at the induction step here. So we iteratively compute the rest of the nodes. For example, if we are trying to calculate the probability of this green node over here, we need to sum over all the preceding states and their alpha IT value, which we calculated in our induction step. And then we would do the transition probability and the emission probability, as we have seen. So for example, let's see if we can make sense of this first line over here. So the 0.08 is alpha 1, 0, or like the being yeah. So and then the transition probability here 0.4 should be the transition probability of going from disgusted state to a disgusted state. So yeah, so if you're in a disgusted state, you have the probability is 0.4. And then we multiply that by the emission probability of frog, given that you are in a disgusted state, and this will be coming from the emission probability table. And similarly for this, here there's 0. It could, but this here we're just focused on an illustrative example. So I mean, the same question could apply to when you're calculating gradients in a computation graph of a neural network. But let's not focus on that here. This is just an illustrative example of the mechanism. So this 0 over here is essentially signifies that the transition probability of going from an unhappy state to disgusted state is 0. So we can verify this if we go back. Yeah, so So here we can see that there's no arrow from this unhappy state to the disgusted state. So it's a 0 transition probability. And that is signified by here. And the last one is we start with 0 probability. So everything else is moot. And this is the probability that we see over here. Okay, so yeah, so essentially, yeah, so we do the same process for all the nodes, and we compute the final column, and we're ready for conclusion, which is we just basically sum over the last column values, and this is our example. This is our answer. Okay, so the forward procedure basically improves on the naive approach because it uses dynamic programming, and it's computationally feasible. Note that we could have done this as easily if we had gone backwards in time, but probably it would be a little bit less intuitive, but we can do that. And that is the ideation of the backward procedure, which is essentially this forward procedure done backwards. But we'll not be talking about it in this lecture. I think this is a good place to stop for this lecture. And I would like to spend some time talking about assignment 2 for whatever time we have left. Okay. So let's stop at slide 46. So I don't have that poll option being a co-host of this meeting, but if I could maybe see reaction with like thumbs up to indicate if you have already started on assignment 2, or at least you have did a first pass on the handout, so that it's relevant to the conversation here. So can you please give a reaction like thumbs up or cross whether you have taken a look at assignment 2. Okay, yeah, so I see some thumbs up and some thumbs down, but that's fine. Let me present it in a way so that it's still, I guess, at some value, regardless of whether you have taken a look at it. Maybe I'll just quickly go over the multi-headed attention part, because there were some questions about this in Piazza. And actually last lecture, there was a question, but I didn't have the time to go over it. So I'll just quickly go over multi-headed attention here. Okay. Okay, so I'm assuming that the attention mechanism, I'm not going to go over it, or maybe I could very quickly, like its attention mechanism is clear to everyone, and I'll just extend from there. The only thing that I want to ask, maybe I'll ask this as a question. So, so recall that what we're doing is that we're in a decoder time step t, and we're trying to, we're allowing that decoder to take a pick at all the encoder hidden states. And basically, by looking at all the hidden states, we're essentially getting a weighted representation of the hidden states given our decoder hidden state at time t, and then we are basically concatenate that context vector as our input to the decoder. And so essentially, like, the tension is calculating this context vector. And this TE over here is essentially just the prediction by the decoder of the word in the preceding time step. Okay, so the input at time t is basically a contextualized or a context vector from all the weighted, all the hidden vectors from the encoder weighted, plus whatever we have observed in the last time step. Okay. Just a question to you: what is the, so let's say the dimension. Let's say the dimension of the hidden state vector is d. What is the dimension of this context vector over here, ct minus 1? We can't proceed until someone throws something, so we'll just maintain this awkward pause. So the dimension into t minus 1. So the dimension is just d, right? So the dimension of ct, so dimension of this oh, so it's a question. Yeah, so I'm asking, the question is, what is the dimension of this context vector c given that our hidden state vector's dimension is D, let's say, yeah, so H is has a dimension of 1 by D. Yes. Yes, that's the right answer. So essentially, like the same as the encoder hidden state dimension. So essentially, like the overall dimension of this is 2D because we're concatenating the context vector with our embedding vector dimension. Okay. All right. So that's fine. Let's keep that in our mind. Okay. So we got our context vector. Okay. So yeah. So essentially, with multi-headed attention, what we're trying to do is that each head, we want to learn a few different patterns. And the way we can do this is that for each head, we can assign a weight matrix, which we'll learn. So let's say we have 2 heads, and we basically assign 2 weight matrices for our decoder hidden state vector and decoder hidden state vector and our encoder hidden state vector. So when we multiply this, and these weight matrices are of the dimension D by D over N. So we are basically like, we have a shrinked weight vector. So what does it do? Essentially, like over here, you can see that so what is the, so if you have your W tilde N dimension of D by D over N, or let's say D over 2, if you have 2 heads, let's go with the example where number of heads is 2. And then our dimension of our hidden state vector for the decoder was, let's say, D. So then this guy becomes a vector of size D over 2, right? So you should be able to convince yourself that. So essentially, for example, here on the right-hand side, this is more of a conceptual diagram. So if you have H as our batch of, let's say, some hidden state vectors, each of dimension D, and then we have our a weight, and then we get our output as M by D. And in multi-headed attention, we essentially have 2 weight matrices, but we have shrinked the dimension by half, or by the number of, like, D over the number of heads. And in this case, and then we concatenate it. And so notice that the output remains the same dimension as we had with a single head attention. However, now with multi-head, with two attention heads, we have packed more information. We have packed to learn patterns, let's say, from the same input, instead of just one pattern that we learned with our single head attention. And that's essentially the idea. So if we had 4 heads, we'd have, like, the output would be the same dimension, but we'd have like 4 vectors that are patched together to get that output context vector. That's essentially the idea. So in your assignment, or in this example, what we're doing in the first step is essentially we are sort of doing a linear transform of our hidden state vectors into a shorter dimension. And then we're using the attention to get a context vector, which is also the shorter dimension. And over here, we're basically concatenating all those context vectors. Let's say if we have 2 context vectors, then we concatenate the 2 context vectors. And essentially, that becomes our output. So here, you should be able to convince yourself that this question mark is a D. Yeah, so yeah, okay, so that's a good question. So essentially, yeah, that's the idea, that each head will attend to all the encoder states and the entire hidden state for all the encoder hidden states. But we are essentially, you can think of it as that for each of the heads, we have a different weight parameters or weight matrix that we're learning. So this W1 and W2 would be different. So essentially, the compact representation would be different, because, like, we're learning different weights for each of the heads, essentially. So yeah, so basically the idea is that each of these weight matrices would capture different things, and that's why the line attend to different things for a given time step. And I mean, so for example, as a concrete example, if you think about the language model architecture BART, it usually has like 12 heads. The transformer architecture has like 6 heads. So recent research shows that there's some research made about like, okay, so what are each of the heads attending to? So for example, like one head would attend to parts of speeches, one head would attend to like it's a nouns and pronouns and stuff. So things like that. And not all of the heads are equally effective. So it was also found that some of the heads learn something which are not very useful. So anyway, the idea is that you know, we are learning, we're trying to learn different weight parameters for each of the heads. Okay, so I think okay, so I will, can you see my screen? Okay, yeah, so I'll end the lecture over the lecture here. Those of you want to stay back and stay back for a few more minutes. I'm just going to go over the starter code very briefly, but this is the conclusion of the lecture. You're free to leave, but if there anyone staying back, I will just go over the starter code very quickly with you guys. Okay. Thank you for attending, and I'll see you after the reading break.